Hey guys, welcome back to Genius Learning. Okay, in this video, I want to show you how to find the angle when it's not given. And I'm going to be doing my way over here, which is with vector triangles and using the vector equation. And over here, I'll be doing it with some kinematics, and I'll be manipulating some equations, some kinematic equations to show you how it's done a different way. Okay, so let's take a look. We have this football player who kicks the football at an unknown velocity, right? We don't know the angle, but what we do know is that the goalpost is 11 meters away, and the goalpost he needs to clear, the bar right here, is 3.5 meters above the ground. Okay, so the question asks, find the minimum angle above the ground needed to clear this bar. So below that angle, the ball will never clear the bar no matter what, or how fast it's kicked. And so that's another way of saying that this is going to be our maximum height. Okay, so if we need the minimum angle just to clear it, that means that this is the highest point. Okay, so with that fact, we can begin. So I'm going to start doing it using kinematic stuff, and then I'll show you the way that I've been doing it over here, so you can kind of see both, and you can choose what you like. So I'm gonna label the steps here, okay? So first, since I know that this is the highest point, right? I'm gonna use my vector equation, VF final, in the Y. So let's just write the general equation. VF final, V initial, plus AT, right? I can either choose X or I can choose Y. And since this is my highest point, I want to choose V final in the Y, because I know that the velocity final in the Y is going to be 0. Okay, so the velocity initial in the Y and minus GT. Okay, so I want to use this and take advantage that this is the highest point. Okay, so that's V final in the Y, and the angle here is going to be the same thing as this angle here, which is V initial, right? And then coming down here is gravity times time. So this is the same angle here as this one in here. This is our vector triangle. Okay, so setting this equal to 0 allows us to solve for time. Okay, so time is going to equal, now remember that this here, V initial in the Y, is the same thing as saying V initial sine. So when I rearrange everything, I'm going to have V initial sine theta over G. And this time represents the time at max height. Okay, that's important, because telling us that we need the minimal angle just to clear it is a sneaky way of saying that this is going to be the highest point, which allows us to use this equation, which allows us to find this formula that we're going to use here. Okay, so now for step 2, I want to use my vector equation. Okay, so I don't memorize the kinematic equations. I just memorize these two things. So this is the different way to do it. It's just that I'm using my notation, but you can just use the kinematic equations to find the same things. All right, so for this one, I want to solve it for Y. Okay, so I'm going to have here the change in y, right, which is y final minus y initial. Here I'm gonna have v initial in the y times time minus 1/2 gt squared. We know that v initial in the y is the same thing as saying v initial sine. Okay, so I'm gonna do the change in y is equal to v initial sine. I'm gonna leave a space where I'm supposed to put the time. Then I'm gonna do minus 1/2 g, and I'm gonna leave another space where I'm supposed to put the other time. Okay, so I think you can see that this expression right here, we don't know initial velocity, we don't know the theta. Okay, but we do have this expression for time at the max height. And so using this displacement equation, this displacement here, which is dy, right, represents how high this piece is right here, which is the max height. And so it makes sense that we're going to use the time at max height in an equation that is going to represent our height at max time. So we're going to put this equation in here. Okay, and then on this side here. And now let's solve that out. Okay, so we're gonna keep this side here, change of y. Combine these two, we got v naught squared sine, lost the theta there. Okay, so sine squared theta over g minus 1/2. There's 2 g's down here, there's 1 up here, and so 1 remains on the bottom. And up top we got v naught squared sine squared theta. Okay, and so here we have the same thing, so it just looks like 1 minus 1/2, which is going to be 1/2. So let's combine that into here. Delta y is going to be equal to v naught squared sine squared theta over 2g. Okay, so this is the expression that we are looking for, right? Which tells us that the max height is going to be equal to all of this, right? So let's look for, so this is going to be a little bit tricky. This is kind of why I don't use this approach, but it's good to see it because you wouldn't think about it, you know, I'd never thought about it. So let's solve this equation for v initial sine theta. Okay, so we're going to move the 2g over here and we're going to get rid of the squared on top. And so I'm going to change this to 3.05 because that's what it is, right? The change in y, which is that height right here, is 3.05. So I'm gonna have 3.05, right, for that. 2g is gonna go over there, so 2 and then 9.8, and we're gonna be left with both of these terms squared, so we're gonna square root it on the other side also, and now we're left with v naught sine theta. Okay, so you should be able to recognize what this term is right here. All right, so that's our v initial in the y term. All right, so let's leave it in this notation, but just know what it is that we aimed to solve for. All right, and this number here is going to be 7.73. Okay, so we can save all of this here. Now let's go on to step 4 or step 3. Okay, so step 3. If we look at our time from step 1, we have here v initial sine theta and what we solved for was v initial sine theta. Okay? G we already know. So let's solve for this time at the max height. So t is equal to v initial sine theta, which we found here to be 7.73, right? Over g, which is gravity, 9.8, and leaving us with a time of 0.788 seconds. Okay, so we expressed T max as V naught sine theta over G, and when we solve for our height equation, right, at max height, we remained with the same expression and plugged it back in. And so now we're here. So this is the time at max height, okay? This is at max height. Okay, so this was the expression, this is the actual value, right? So now, step 4. All right, so step 4, and remember, all of this is to find the angle. Okay, so our objective in doing all of this is to find this angle, and that's it. Okay, so now step 4, let's use the vector equation again. Okay, and this time let's solve it for x. So we're gonna do the change in x is equal to v initial in the x times time, and we already know that this term here, acceleration in the x, is gonna be 0. So I'm not gonna write it this time. All right, so we're left with this, and we know that v initial x is the same thing as saying v initial cosine theta, right? We bring the t over here, and we have the change in x, right? So let's bring the t over here by dividing. We have the change in x divided by t at max height. So I'm just gonna write max height here, and we're left with v initial cosine theta. All right, so here, this change in x represents this change in x that goes all the way to the goalpost, all right? And we wanna know the velocity initial and cosine term there. We know that the time there, which is here, is at maximum height, right? Because the ball just clears the goalpost, so we know that that's max height, and so we're using the right time and placing it here. Okay, and we're gonna leave the expression just like this. Just like we did with the v initial sine theta, we're gonna leave the v initial cosine theta. Let's fill in this side. We got 11 meters on the top, divided by 0.788, which is the max height, equals v naught cosine theta. And finally, 13.9 meters per second. Meters per second is equal to v naught cosine theta. Okay, now we have everything we need in order to solve for the angle, which was the entire goal of this problem. So step 5, we're gonna do tangent, right, which is equal to sine over cosine. So we're gonna take this term here, velocity initial sine, and we're gonna take this term here, velocity initial cosine. We cancel out velocity initial, and we have sine over cosine, or we can use the values that we were given. So here we have 7.73 meters per second, and for the cosine part we have 13.9 meters per second. And so if we do inverse tangent of these values, okay, we can finally get an angle of 29.06. Okay, so that was the entire goal, to solve for this angle given only the distance away from the post and how high the post is, and also the information that we need an angle that's just going to clear this post. All right, so you can see it's pretty involved, and I want to show you guys an easier method in solving these types of problems. So everything that I've been doing is to show you shortcuts like this. Okay, so we've moved on. Let's move on to now my examples, and so how I do it. And let's get this guy over here kicking the ball on this side now. Okay, so what we're gonna do is use the vector equation, right? So the triangle plus 1/2 AT squared. Okay, so let's use the triangle, and this right here is going to be our final position, right? Because we just are interested in this this barrier here. This is like where the time is at that it takes to get here, and this is 11 meters of length. Okay, so we're going to draw our displacement vector straight to where we want it, which is going to be here at this final position, and this is D vector. And then we're going to draw our vector line for velocity initial times time, which goes up to the goalpost, right to it. Okay, velocity initial times time, and then downward always is the gravity term. So 1/2 GT squared. Okay, so just by drawing this triangle, I can see that these two things are equal to each other, right? Because the length of this vector here is the size of the goalpost, and so what I can do is set them equal to each other. All right, 1/2 GT squared equal to 3.05 meters. And if I solve for time, I'm gonna get the square root of 2 times 3.05 over 9.8, which is gonna give me a time of 0.788 seconds. So that's the time it takes to get to the goalpost. And so that was discovered on this side on step 3. And so I can find it in 3 lines, right? So all this work here was needed in order for us to find the time it takes to get to this post. All right, now let's go into this one here. So 11 meters is where the goalpost is. Okay, and so here I want to show how we're going to get the angle. So let's draw our vector triangle like we usually do for our displacement vector. Okay, so our area of interest is going to be at the goalpost now, right? Because we're no longer interested in the time, right? I have to preserve this angle now, so I needed to match up. Right here I didn't need to because I just wanted to make these sides equal, but here I'm gonna need to. So my displacement vector, the first one, is gonna go towards the area of interest, my final position, which is going to be at the top of the goalpost, and then velocity initial t, right, always follows the initial velocity vector and goes directly above the final position. So velocity initial t, and can't forget that gravity vector is always going downward. Okay, so we stop here because the length of the bottom part, which is this, is 3.05. All right, so if you already see, in order for us to use this angle, we need to use this entire triangle here, which combines this height here with 1/2 GT squared, like we've been doing. We have our 90 degree for our triangle, and so now we have our adjacent value, right? So I think about cosine or tangent, but I have these values, so let me use tangent. So tangent is going to equal opposite, so the entire side is going to be this vector here plus this length over adjacent, which is 11. Okay, and I know the time it's gonna take to reach this post because that's the max height. So I have all the values here. If I solve for theta, I'm gonna have tangent inverse of 1/2 9.8. The time for the max height 0.788 squared plus 3.05, everything over 11, and we put that into a calculator. We're gonna get theta is equal to 29.06 degrees. Okay, so 1, 2, 3 lines to get the same answer, and that was from here to here. Okay, so this entire first part, 1, 2, and 3, we can find it in 3 steps using these triangles. And for the angle, right, 4 and 5, all of this, we can just find it using 3 steps if we cleverly choose our triangles to match and become 90 degrees and use our vector equation in order to set it up in a way that we can just solve it faster and try to avoid, you know, all this confusion here. But there's both ways so you guys can see it. And this guy was supposed to be down here kicking this one. All right, so you guys check it out, see which one you like best. I mean, obviously learn both, and let's work on some more examples in the next videos.